It's my pleasure to announce the talk of Elena Nokhrina. The title you can see here. Well, I guess the talk will be more general than just the core shift, and it's probably the real introduction to astrophysical part of our school. And please.
Mm-hmm. Thank you very much. My name is Elena Nokhrina. I'm working as a senior researcher in Lebedev Physical Institute and also as a head of laboratory of relativistic astrophysics at Moscow Institute of Physics and Technology. And if you are interested in joining our laboratory as probably a PhD student or maybe postdoc, you are welcome to contact me. I will later leave my contacts. So yes, thank you. I'm going to give some general review, and here is the outline of two of my lectures. So as this event, this great event takes place at Lake Baikal, and which is more nearby Baikal GVD, Neutrino Telescope, I wanted to make some focus on astrophysical jets in connection with possible neutrino sources. So my talk will be this slide. Well, anyway, so I would give some very brief history overview of connection between high-energy neutrinos and blazars. Then I will provide an overview of active galactic nuclei. I hope to give you some sense of how plasma accelerates inside the jet, what's the composition of jets, which is a mystery. What is the distribution of electric, magnetic fields, and how this central engine, the black hole, works. And after that, I will just remind you I will remind you on some things about synchrotron emission, and we will touch upon the effect of core shift just as an instrument of as a possible instrument of assessing the neutrino origin location inside jets by the dilations of neutrino arrival and arrival of flares in radio. So let's proceed. Some general information, not about jets. Well, I will say a few words about jets. Well, jets are observed actually for quite a long time. It's now more than 100 years ago when the first astrophysical jet has been discovered. It was reported in the paper by Curtis in 1918, so it's 107 years ago, when the author wrote that there is a strange ray of light pointing towards or out of the galaxy, our famous galaxy M87. However, quite a lot of time went before people understood that those strange objects are actually extragalactic sources, and the first redshift has been measured, if I'm not mistaken, in 1964 for the source 3C273. It's another very famous source. And after that, it was understood that those strange stars with probably rays are extragalactic and extremely powerful sources. But the history of possible connections of active galactic nuclei, of blazars with neutrinos, are very young. So I found in a nice overview by Marcus Böttcher, it's an astrophysicist, that the actually detections of extraterrestrial neutrinos with energies more than 50 tera electron volts began since 2012, and that was at South Pole by the Ice Cube Observatory. In 2019, the first detection of even larger energy, more than 100 tera-electron volts, was done by Baikal GVD, and I guess it was the first astrophysical high-energy neutrino detected in northern hemisphere. Direction, no particular direction along the galactic plane demonstrated that the sources of high-energy neutrinos are probably extragalactic, and the overview is in paper by Troitsky et al. 2015. But actually, almost 50 years ago, in 1977, Berezinski already has suggested that AGNs, they are so powerful and extreme sources that they may produce neutrinos which, with high energy, which might be detected possibly at Earth. And the real connection between blazars and as a possible source of neutrinos happened on the 22nd September of 2017. The detection of neutrino at 290 tera-electron volts by Ice Cube. Which was more important, it's not only that it was in the direction of famous blazar, famous after neutrino discovery, TXS 0506 plus 056. But it was important that at this time, around September, October of 2017, this blazar was in a high gamma ray flaring state. So that actually suggested that maybe those events are connected. There was found an archival data which showed that actually something like that happened before, and that established the connection between, in the literature, blazars and neutrinos. And in 2020, so it's only 5 years ago, the statistical confirmation of coincident location of bright radio blazars with neutrino sources has been discovered by the team Plavin et al. And others. Let me tell you about the physics of the AGNs and their subclass blazars. So here I'm trying to show you the most general picture of famous AGN M87. So first of all, let's give a definition. Active galactic nuclei is a compact central galactic region with power output which generally exceeds the total output of all the stars in a galaxy. So the excess may be from 10 to 1,000 times. And here is the most general view of M87. We see some wisps, some bubbles, probably blown by the jets. And here is the central part. And here you can see the scale. It's 25 kiloparsecs, so it's quite large. And the image was taken at 90 centimeters, so it's radio band. Then let's look at this picture. This star corresponds to this. So the scale is smaller. Here is 800 parsecs. And so you must understand that this almost straight, very well collimated jet lasts for hundreds of parsecs. So that's actually amazing. It's also radio, 20 centimeters. If you zoom again, you see well, also for radio, not very usual picture, but here is some central part, and you see this blobby, straight, well-collimated outflow with some brighter features, probably standing shocks, and the scale here is 400 parsecs. And if we will zoom into the very central part, so here is 0.8 parsecs, and here is 400 parsecs. You will see the classical radio image of radio galaxies of blazars. So you see mainly a bright central feature, which is called radio core, and then some blobby pattern obtained at 2 centimeters. So it's the innermost part of a relativistic jet. Now let's proceed. Sorry. So what do we need to launch these jets? And here I will make some sidelines on how some properties of active galactic nuclei are obtained. So this is a nice picture. It looks nice, but it's totally not non-physical. So here is what we need to launch a jet. First of all is a supermassive black hole depicted at the very center. Now, usually we estimate the masses of supermassive black holes residing in the centers of AGNs as being from 10 to the 6 to 10 to the 10 solar masses. It is very nice to know the mass of a black hole because we can easily calculate the gravitational radius. And after that, we will understand quite a lot of physically meaning parameters for this black hole. However, actually, we don't have a very precise methods for measuring black hole mass. And here I wanted to just give a little overview of how this is done. There may be direct methods, and they actually, up to just a few years ago, they were applicable only for the most nearby sources. In this case, if you can resolve moving stars or some clouds or some gas flows nearby the central black hole, you can measure their velocity dispersion by redshifts. You can directly observe the distance to the center, and so you can imply the mass of a black hole. And just several black holes masses of just several black holes has been estimated by this method, including our galaxy, where we just observe the orbits of particular stars. That was done for M87 by the gas flows. And the result is, quite established. The result for M87 corresponds to what we measured by observing the shadow of a black hole. Just a few years ago, the gravity calibration using VLTI, so it's very large telescope interferometer, which is no, I didn't put picture here. Okay, it's situated. It's 4 like 8 meters telescopes situated in the perfect astronomical conditions in Atacama, Chile. So it's high, it's dry. They measure even for quite distant. They are able to measure the distance to the population surrounding black hole, even for large distances. And here I provided a picture for It's a paper of 2022. Here is the result for this source. Never mind the name. It is important that it is situated at the redshift 2.3 to 5. So that's quite far away. So what they measure the velocity dispersion, and which is more, they may separate the photocenters of approaching line, which is depicted here by blue light, and of red line, which corresponds to the going from away from us lines. And actually, they employ also modeling of clouds moving around the black hole. But if you know the velocity, you know the distance, then you know the mass of the black hole. So that's quite a precise method. But it, of course, requires quite a sophisticated and long-time observations. And another direct and reliable method for estimating black hole mass is so-called reverberation mapping. So it also uses this simple relation first look at this picture. It employs the following. I will show you this picture also later, but here we can see the following. This is a central black hole, supermassive black hole, sorry. This is a torus from which the gas accretes onto a black hole. This is a thin accretion disk, jet. And we know from the observations that there are some clouds which produce the so-called broad lines region. So we observed lines when these clouds are illuminated by the emission from the center, and they are broad. That's because clouds are situated relatively close to the black hole, so they must have large velocities, and hence the broadness of a line. So you can measure. You can measure the width of a line, so you understand the velocity dispersion, and then you may carry very special observations. When you observe a flare in ionizing continuum in X-rays, that's from the inner part of the disk if some flaring event happens. And after that, when this ionizing continuum illuminates the, well, actually here, the broad line region clouds, you will see the amplifying of the line's amplitude from this one. And measuring this delay, you can estimate the position, the radius where those broad line regions clouds are, and so you can and so you can estimate the mass of the black hole. And also about, probably a dozen or a few dozens masses has been obtained by this method. Other black hole masses have been obtained by very indirect methods. So it may be a reverberation mapping proxy when velocity is measured directly because it's easy, but this radius position of broad line region clouds are estimated using some correlation. And also there are a lot of correlations established on nearby sources like black hole mass and galaxy stars velocity dispersion. Usually they provide also black hole mass around 10 to the 8, 10 to the 9, but they are not quite reliable because the error may be like an order of magnitude. So, so what we know about the masses of black holes. Now, the next constituent of launching a good jet, we have to have a magnetic field. For this, we actually need, we all know the theorem that black holes have no hair. So the magnetic field can be brought into the vicinity of a black hole by the accretion disk. So there are two different scenarios. I'm not sure whether which one is preferable now in the literature, in the papers. In one scenario, it is assumed that the mean galactic magnetic field are just frozen into the infalling matter and concentrated and brought down onto the gravitational radius scales. Another possible mechanism is a generation of magnetic field in the disk itself. It's some kind of mechanism like alpha-omega dynamo in the sun, and which is important. We think that the highest magnetic field can be gathered around around the central black hole is about 10 to the 4 Gauss. While in M87 we measure a few tenths of Gauss. And let me just say a few words about how the magnetic field is measured. Well, this method, about this method I will be talking in the lecture 2. So some measurements allows measuring magnetic field, making some assumptions like in the region of a few parsecs, and then assuming some relation on radius, extrapolate magnetic field onto gravitational radius scales. And here is the probable result for NGC 315, where the expected magnetic field is around 10 to the 3 Gauss, so it's lower than 10 to the 4. Another method is, well, it was obviously applied right now for one source, and maybe it will be applied to our galactic center. It's a direct image of polarization of a bright ring around M87 black hole, which is designated by the star. And modeling allows to understand that the magnetic field there is about this value, so that's quite low. So we have a supermassive black hole. Suppose we have a magnetic field brought into its vicinity by the accretion disk, but that's not enough. We also need the black hole to have quite a high spin. So we expect that in the centers of AGNs are situated Kerr black holes with angular momentum, and the dimensionless angular momentum is from +1 to attains the value from +1 to -1. Numerical simulations from private communications, I was told that if you have this dimensionless spin less than 0.1, the jet isn't launched. So, this is an accepted lower value for a dimensionless angular momentum or black hole spin, but that's not actually established. It's just, you know, the result of numerical simulations, whether we launch jets. So, if we have now a rotating black hole, then it drags the time-space around it. and also the magnetic field with it. And the magnetic field initially poloidal, and poloidal means in axisymmetric systems, poloidal means two components except toroidal. So if you use cylindrical coordinates, then the vector with r and z components are poloidal, and phi is toroidal. So initially poloidal magnetic field starts making loops, and we have presumably strong toroidal magnetic field component. So if we have such a component, then we must we understand that we must an electric current I flowing along a jet. And this means that actually we will need a plasma filling a magnetosphere. So, sorry. Well, anyway, so we assume that there is some mechanism of producing plasma in the at the very base of a jet in the vicinity of a black hole. The particular mechanism is unknown because some simulations show that we can probably supply enough electron-positron plasma by two-photon conversion of photons going from the inner parts of an accretion disk. Maybe that's enough, but actually that's one of the big questions which we still don't know the answer to. Also, we actually do not know the composition of the plasma. Usually we work with electron-positron plasma just because it's convenient, and that's what you expect that is produced by the two-photon conversion. But there are works that, some estimates shows that probably we need presence of some protons there just to carry enough energy. And the only estimate on the number of present protons in a jet I've seen in the work by Andrzej Żarski, who estimated it to be no more than about 1%. So we have electrons and 99% of positrons and only 1% of protons. But that's important because we need protons to produce neutrinos. So if we somehow filled the jet magnetosphere with plasma, then we assume, and usually it is probably quite correct for cosmic plasmas, that we have an ideal plasma with a freeze-in condition here. And this means that we have a poloidal component of magnetic field, toroidal component of magnetic field, and we have here an electric field pointing like this, using this equation. Omega here is an angular velocity of rotation of field lines. And if we have electric field and magnetic field, we have the pointing flux flowing inside the jet. And I will show you a little bit later, but in most part of the jet, toroidal magnetic field component dominates the poloidal component. So the flux mainly, pointing flux mainly directed along the jet and outside from the black hole. So let's proceed. Okay, I will talk about this later. And here is, the picture is bad. Okay, I will return to it later. So how we model the jets? We use ideal axisymmetric magnetohydrodynamics. as an analytical approach, and it's also used mostly in, like by Komisarov, in numerical simulations also. So the main value in this approach is so-called magnetic flux function. Due to axisymmetry, it depends on r and z coordinates only, and it defines as follows. Let's take some circle with situated at the height at the coordinate z with radius r. It will be a circle, and we can take any surface for which this circle is a boundary. And let's calculate the flux of a magnetic field through this surface. It will provide you the magnetic flux as a function of r and z. This is what we actually need to know when we model the jets. This function can be obtained by solving a system of nonlinear MHD equations, and I'm not even writing them here. They are Grad-Shafranov equation, which physically means the force balance perpendicular to magnetic surfaces, and Bernoulli equation, which defines electromagnetic field and plasma properties along the field lines. So if somehow these equations are solved in different approximations, like in cylindrical approximation or in some asymptotic approximation where the jet very far from the jet origin, or numerically. But what we will need is that if the flux function psi of Rz is known, then we can easily express magnetic and electric field as follows. The poloidal component of magnetic field is just nabla psi over 2pr. R is a cylindrical radius. So we see here is the cross product with toroidal unit vector, so it's really a poloidal component. The toroidal component, it's written here, and it is totally defined by the function I. It is the total electric current flowing through any surface inside a particular circle. And electric field is defined by some function which means actually field line's angular velocity omega f over 2pc, and also nabla psi. This function defines the main length scale in MHD modeling, the light cylinder radius. For example, if some part of a jet is connected to the black hole magnetosphere, and we may assume that this angular velocity is constant, like set equal to omega naught, then there appears a length scale, so-called light cylinder radius, which is speed of light over omega naught. And we will need this actually for following estimates. Sorry, and no, that's okay. And now we will jump to the velocity of plasma inside a jet. So what we observe, to show you, I used this picture. So it's not relevant to this talk. The x-axis is not relevant to this talk. What we need to look at is maximum apparent jet speed in units of light. So those are the observations, and I will now describe, just a few slides later, I will describe how they are carried on. The observed velocity of bright features in jets can be 10 speeds of light, or 20, or 30. This picture was taken from an extensive study of kinematics in jets by Lister et al. 2019. Why do we observe the superluminal motion? That's quite a simple problem, so I decided to include it into a lecture. Here is depicted how we measure the apparent velocity of something in jet. So there may be some bright feature observed by us at time t arrival 1. Then if we look at the same jet about a few months later, or probably a year later, we can see the bright feature at the time t arrival 2. And if we by some methods know that this is the same blob of light that emitted, that produced emission at this time, then we can measure the speed as follows. The first, initially, blob emitted light at this time, which we take as 0. Then it moves along a jet at a distance r, and now here all times and distances are measured in observer's frames, so no boosting right now, no Lorentz transformations. So it's r in our system and emits at t emission 2. Then t emission 2 is equal to just r over v, and arrival time from this blob is L is a huge distance from the jet to the observer, to us, plus r cosine theta. Theta is a viewing angle over c. And the arrival time from this blob is an emission time plus L over c. What we measure? We take this time, which may be a few months or a half of a year or a year, and we take this distance. Suppose we know it. We measure angular distance, but if we know the luminosity distance or angular distance to the quasar, to the AGN, we can calculate it into the physical distance. We measure this distance on the picture plane. So it's distance r sine theta over difference in arrival time. And if you will use these expressions, you will get this, which means that difference difference in arrival time is equal to difference in emission time multiplied by some kind of Doppler factor. Actually, it's a classical Doppler factor without Lorentz factor. And we measure the apparent velocity using this as the real velocity sine theta over 1 minus beta here is v over c cosine theta. And actually you can see that for small angles, and when the real velocity beta is quite close to 1, we would observe large apparent velocities up to actually 100 of speeds of light. But you can also recalculate this expression back and estimate this velocity v as a function of v apparent, or directly calculate the Lorentz factor of a plasma in a jet. So from these observations, we know that something, plasma, we think flows along a jet with relativistic speeds with Lorentz factors up to about 100. So that's quite fast. Now, this is just a picture of which I wanted to show you by measuring the position of these bright features. We measure the apparent velocities in jets. And here are the results of direct estimates. So you see the separation from some bright feature, which is called core, stationary feature, that's separation. And that's the periods of time when you measure it. So you just follow the bright feature for like 5 years or some even 10 years and can estimate the corresponding velocity. Okay, now quite a lot of time and efforts has been put into obtaining this result from the equation I mentioned here. It follows that the bulk motion Lorentz factor may be estimated as quite close to this expression. So it's squared poloidal magnetic field plus squared toroidal magnetic field minus squared electric field over b phi squared. Actually, this expression, it was first obtained in 2004 by Vlahakis and then repeated in 2007 by Komissarov et al. And in 2012, I guess, by Chekhovskoy. This expression means that the MHD motion of plasma, and now you must understand that that's quite a complicated story, because when you studied in university and you studied how the particle moves into a given crossed electric and magnetic field, it's not the same story as with magnetohydrodynamics. Because in magnetohydrodynamics, you don't have a set electric from somewhere from outside, set electric and magnetic fields. They are established by the moving currents, and then that means charges and particles, while these fields themselves affect the motion of these particles. So the problem is quite complicated, and that's actually amazing that we can draw this result, which means that the motion, a full MHD motion in jet, may be viewed as a motion in crossed electric and magnetic fields if we know the solution for a jet structure, if we know those fields. You may notice here that here is written just a magnetic field in a plasma proper frame. So if you move into a frame where electric field vanishes, and in MHD magnetic field is always slightly larger than electric field, then in this frame you have a reduced magnetic field but no electric field. So that's the frame where the plasma acceleration, charged particle acceleration stops. No electric field. We know from the observations that the jets are relativistic, just because we observe superluminal motion. And that means that magnetic field is almost equal, just slightly bigger than the electromagnetic field. Otherwise, the motion would not be relativistic. And this means the following. Now I have this slide. So which field components we can estimate easily? Let's look at the absolute value for E and absolute value for poloidal magnetic field. Here, let's return here. Here is electric field, magnetic field, poloidal magnetic field. And their ratios, you see that here nabla psi vanishes, and you just have this expression omega f r over c, so it's r over light cylinder radius. Which means that electric field almost everywhere outside the light cylinder radius is quite small. For a black hole mass, about 10 to the 9 solar masses, it may be something like 10 to minus 4, 10 to minus 3 parsecs, as we believe. While the jet width may be from 1/10 to a few parsecs. So this scale is quite small, and almost everywhere in jet electric field dominates the poloidal magnetic field. But then, if it is much greater than the poloidal magnetic field, and the fields, their amplitudes must be almost equal, then we arrive to conclusion that the toroidal magnetic field must be almost equal to toroidal magnetic field must be almost equal to the electric field. And after this, we arrive to this important relation that absolute values of B phi over BP is equal to R over light cylinder radius. So outside the light cylinder, the toroidal magnetic field dominates the poloidal component in the AGN frame. I must underline this. And here is the picture of some solution of MHD equations. That's a strict solution. This solid line is a poloidal magnetic field. Dashed line is a toroidal magnetic field. And the dotted line is an electric field. So you see, toroidal and electric field are almost equal. And X here is this ratio, R over light cylinder radius. When X is equal to 1, these fields start dominating the jet. So actually my picture of very tightly, very tight toroidal magnetic field describes exactly this situation. Now let's proceed to the acceleration. What we know is that from numerical simulations and from analytical solution that plasma in jet, it doesn't go straight with Lorentz factor like 50 or 100. It is accelerated along a jet. And we have here, this is a result of analytical solution, a region of effective plasma acceleration when Lorentz factor grows linearly within a cylindrical radius, like this. And actually we can see from this equation the following. We must have this relation if the poloidal magnetic field is much larger or of the same order than B phi squared minus E squared. So in this case, we may neglect by this term, and we know this relation. It's exactly this. And thus, we have an effective acceleration with Lorentz factor growing quite fast. Actually, this growth continues until the half of maximum Lorentz factor is reached. And at this point begins a saturation of acceleration, and we know that this term, B pi squared over B phi squared, cannot dominate. And so in the region where acceleration almost stops, when a jet attains almost constant Lorentz factor, B pi squared must be much less than B phi squared minus E squared. And this is quite important because, well, just let me show you. The previous picture was an analytical solution, And here is the results of numerical simulations for the Lorentz factor as a function of radius in units of light cylinder radius. So here we see effective acceleration and then saturation. Sorry, no. Here is the result. So we may now note the important result. When we sit into to a plasma proper frame, then the major velocity is poloidal. Then we know that the poloidal magnetic field value does not change with such a transformation, Elena jet. But toroidal magnetic field changes. Its value in a plasma proper frame, square of it is equal to this. And this means that, when the jet is effectively accelerating, then in a plasma proper frame, poloidal magnetic field dominates the toroidal magnetic field in this frame, while in the AGN frame, we know it must be opposite. But when the acceleration stops, almost stops, then the plasma proper frame toroidal magnetic field starts dominated the poloidal component. I must also show you these pictures. Let's now think about the jet shapes. What we see in the first pictures, we have seen nice conical jets. But is that true? And quite a recent result. This is a result which was first discovered in 2012, so it's 13 years ago, by Asada and Nakamura, 2012. And here is the update of their result 6 years later. Look at the following. What depicted here is a measured jet width. It's on the y-axis versus distance along a jet. Here is x-axis. So it's width as a function of length. It is drawn in logarithmic scale, and we know that in this scale any power laws will be straight lines, but with different slopes. So it was discovered that the slope of the jet-shaped boundary changes at some distance. So here it goes like a parabola, so jet width d is proportional to the square root of a distance r along a jet, and here it turns into the cone, which we can actually observe. Later, this result has been repeated for a dozen more sources. And now it is, I think, established that probably this is the common feature of all the jets, that they launch starting with some kind of highly collimated parabolic shape and then going as a cone. This effect was discovered only for nearby jets because of finite resolution of interferometry. And was discovered for quite many sources, but one of the important results that this change in a jet shape occurs somewhere between 10 to the 5, 10 to the 6 gravitational radii. And we provided explanation for this. One of the possible explanations And here I'm going to tell you about it. Now some excursion into the history. One of the important questions for many years, and it's probably still now, is how jets are collimating, because it's a huge jets having a huge power. It's like 10 to the 42, 10 to the 45 ergs per second. But we see them, as I just showed you, very narrow cones, very narrow lines for hundreds of parsecs. For quite a long time, the community, the astrophysical community, thought that maybe self-collimation is at work, and the self-collimation is quite simple. If you have an electric current flowing in one direction inside a jet, then it just attracts, and the Hooke stress, the toroidal magnetic field around this, this electric current collimates the jet. Now this point of view actually moved from this into believing that the ambient pressure plays a major role in collimating jets. So let's look at this cartoon. Probably there is a Bondi accretion onto a black hole, so it's spherical accretion surrounding the active galactic nuclei. And in this case, actually, the parameters of this gas, which accretes spherically, symmetrically onto a black hole, it has been measured for several sources, and one of them is again M87, and it seems that parameters of this gas are enough to collimate, to suppress and hold the M87 jet. So let us assume that we have some ambient medium with pressure proportional to the, here Z for is a distance along a jet, proportional to Z to minus 2. So the power index around 2 is a classical result for a Bondi accretion. And in this case, let's recall that the jet pressure at its boundary will be mainly not the gas pressure, but the magnetic pressure in the plasma proper frame. Then if we have an effectively accelerating jet, then we know that this expression generally holds, and this relation it's universal for relativistic jets. And if the jet is accelerating effectively, then P is just proportional to the toroidal magnetic field over R squared. Why is it? You have dominating poloidal component over this one, and poloidal component is a toroidal component over R. So that's what is written here. And if you recall that B phi is equal to, proportional to the total electric current I over R, then you have an additional R squared here, and pressure just proportional to the current squared over R squared. R is a cylindrical radius, sorry. And if this function changes slowly along a jet, then you will have the following relation, and for equilibrium across the jet boundary, you will have the relation that R is equal to Z square root of Z. So that provides you a parabolic jet shape. But if the acceleration becomes ineffective, then we can neglect by this in this expression. So this left, only this left, this is left. And the pressure is, in this case, equal proportional to b phi squared over Lorentz factor, which is constant here. And we are left with I squared over r squared, which means that for equilibrium jet in equilibrium with ambient medium, we have a conical jet. So this suggests that what we observe in jets, probably the parabolic jet shape corresponds to effective acceleration when the jet is still accelerates plasma up to large Lorentz factors, and when we observe a conical jet, then the Lorentz factor is more or less established, and we observe the almost maximum plasma bulk motion velocity. Okay, and that was actually supported by several results, both analytical and numerical. This was very surprising because in this work, Commissarov et al. In 2007, they obtained, this result of effective acceleration and saturation was one of the results, but at the same time they obtained that the jet pressure changes its dependence on the distance along a jet around this point, but never mind it. They actually skipped this result, and we discovered it with Maxim Barkov later. In work by 2020, we obtained that the point where the jet changes its shape, it's an analytical modeling from parabolic to conical. This point corresponds about to this point where the bulk plasma motion Lorentz factor growth changes its speed. So it grows effectively here and almost saturates here. There are some very tentative observational evidence for this effect. So this is a jet break in a jet shape in this source. It's by Hada et al. 2018, and about around this transition point, they observe that upstream of this point, jet accelerates, and then it doesn't even stop accelerating, but the velocity becomes very low. And here another result for NGC 315. These dots are measurements of, here is not the Lorentz factor, but the real velocity of jet components. And this is our fit by the analytics, and we see that actually this line shows the point where jet changes its shape, and it corresponds to the stop of acceleration. In the second lecture, I will employ this a lot, so that's why I'm telling you all this. And now, okay, let's stop on this slide. So what I want you to remember is that, well, of course, that jets are outflows of relativistic plasma and electromagnetic field. That quite far on the scales of 10 parsecs, the observed plasma bulk motion velocities are about 10 up to 100. Lorentz factors have values of 10 and up to 100. But before that, in the in the vicinity of a black hole in the scales of up to 10 to the 5 gravitational radius, jet actually is, plasma is accelerating in jet following this law. And in the jet, in the AGN frame, the toroidal magnetic field dominates the poloidal component almost everywhere. But if you move into a plasma proper frame, then poloidal magnetic field dominates the toroidal in the region where the jet accelerates, and farther in the conical jet, toroidal proper frame magnetic field dominates poloidal magnetic field too. So these are the things to remember, and I will actually use these results tomorrow. Tomorrow I will be talking about the jet emission, how we model it, and how we can estimate jet parameters by observing the the emission of jets in radio. So thank you, and I'm ready to answer the question.
Thank you for the nice presentation, and let's go for the questions. Yes.
Thank you very much for the lecture, and maybe my question is very stupid, but if we assume that we write a Hamiltonian for the particles which are going to the jets, and then I assume we should have a term which break the symmetry, and then we have preferred direction, and if we just change the sign of this term, then we are going to have like preferred plane. And if it's not true, then why? And if it's true, then will this object observed?
Sorry, which particles are you talking about?
We can talk about any particles which are in the jets. So they go only in one axis, right?
No, they have actually, well, mainly one axis, yes, but they have a toroidal component, a toroidal velocity component. It's just much lower than the poloidal one. Yes, and if we
change the sign of this term in the Hamiltonian, then we are going to have not preferred axis, but preferred plane. And if it's not true, then why? And if it's true, then if it was observed.
Well, that's an interesting question. No, I cannot answer it.
Thank you.
Who else?
Thank you for this very informative talk. I have a very naive question related to what you said, that you said that maybe most of the component inside the plasma is E plus E minus, with a very small component of a proton.
Yeah.
I thought that the whole thing about neutrino detection requires more protons, hadronic processes that you can see. But just given what we observed with NGC 1068, and just taking the ice cube's full sigma value as the brightest, probably in the next century, we're still going to be the brightest neutrino source. Is this still consistent, what you said about this 1% portion?
Well, that's a big question actually, because I'm not sure. We are working on the number of protons required to see those neutrino fluxes. That's a complicated story because we also must include into consideration how the electromagnetic fields are configured in the possible site. But the protons are probably there, and I think the bigger problem is not only how to have enough protons, because probably we have enough. I'm not sure. That must be, this is a future work and it's ongoing work. But also there is a problem how we accelerate them up to PIF energies, and that's really interesting. And but that's work for future.
Okay, thanks.
Maybe I just add to that 1% of protons still means that they are dominant energetically. maybe
that's
this was not convinced in
I see. That's a number, not
Yes,
rather than
yes,
the energy
not
carried.
Yes,
energy,
yes, yes,
but by
yes.
number.
Yes, by number. Yes, by that's by number, but
So energy-wise-
particle number density. Sorry,
Alright.
and the energy may be stored. The energy is huge, and
Makes
actually, yes. Thank you. The protons are brought. The question of protons are brought into the jets to have the larger power, at least comparable or probably exceeding the power carried by leptons.
Thanks.
Other questions?
So I might also ask a silly question, but if I remember this correctly, jet also depends on the accretion rates and
Sorry, on what?
on accretion rates, and there was signs that this was exceeding the Eddington luminosity. Was this problem?
No, well, I will just a little bit talk about it tomorrow, but the jet emission is highly boosted. Generally we see the jets that, well, we see radio galaxies almost perpendicular to or line into the picture plane. But many bright AGNs, the quasars, blazars, and certainly all those which we observe from the large distances with large redshifts, their emission is highly boosted towards us. Because this relativistic speed, about Lorentz factor a few tenths, and in this case, all the emission produced in a jet goes into a very small angle, half-open angle of the order of 1 over Lorentz factor. So that's a lot.
Other questions?
Thank you very much. I have also a naive question. Beginning from the black hole, if the equations which you mentioned able to reproduce magnetic and electric fields which are needed,
Mm-hmm.
do they? I mean, or because
Well, how close to a black hole? That's actually a question. We think that we may extrapolate, I will be talking about it tomorrow, we think that we may extrapolate our results down to like about a 10 gravitational radius, and we will understand the magnitude of magnetic field. Probably not closer, because just because what we observe closer, maybe it's not a core. I will be talking tomorrow. But yes, we do hope. There are problems with estimating, understanding magnetic fields at the gravitational radius, because the picture I was showing you concerning M87 result when they observed direct polarization, that requires quite sophisticated measurements of measuring the rotation measure to understand the magnetic field. And maybe we may, the high magnetic field are so high that we lose some 2p's in this rotation, and so there are problems with these measurements. Now, what I will be talking tomorrow, it's using core shift and extrapolating magnetic field down to the gravitational radius scale. There is a question whether the jet sustains the same dependence of magnetic field on the distance on the larger scales and at lower scales, and down to which scales what we observe we may call the core, or just because the jet becomes transparent. So we hope that we will be able to tell you, like in a few years, what's the magnitude of a magnetic field, and we even expect that we may report a higher the magnetic field than 10 to the 4th which will be a problem. But there are methods. They have their drawbacks, but I will talk about it.
Okay, thank you. I just...
No, maybe I didn't understand your question.
No. I just wanted to have a kind of a qualitative picture. For example, what makes the electric field? If you have electrically neutral plasma, do we have kind of a capacitor out of the plasma? So what qualitatively makes the electric field, for example?
No, the electric field just appears when we have the plasma and rotating with inside the magnetosphere. So it's produced usually they're used an analogy of unipolar inductor, where you have the rotating sphere with frozen in. Actually, it works mostly for neutron stars, but for black holes probably also. When you have a frozen in magnetic field, you rotate and you connect it with some wire. Then you will have an electric current flowing through this wire. So here is no actually solid sphere with frozen in magnetic field, but when you have a poloidal magnetic field carried by the space-time by the black hole, it produces qualitatively the same effect. So as a conductor, and when you fill the magnetosphere with ideal plasma, then you establish currents and you actually establish electromotive force, which produces the electric field.
Thank you.
One more question from students now. No question from students? Then I have my own. It's actually also a simple question. If you have an external pressure that collimates the jet, how can you be sure that this is 1 over r squared?
No, we cannot be sure. We cannot be sure. We have measurements, some. And unfortunately, for M87, these are -2 power is around this is an analytical result. That's what we believe. The measurements have been done for M87 and just for a few other sources, but on the scales outside the so-called boundary radius. So it's outside like 50 parsecs. It's quite far. And for M87, those measurements of particle number, density, temperature, and so forth, they actually provide that pressure behaves like r to the -1, closer to the boundary radius. So we don't know that. This is an assumption. Now, we may actually add that there is some outflow from the disk with some pressure distribution, but that's, I think, complicates, and since we do not know anything about those flows, like we use these theoretical results, which we are not sure of. So we can use some measurements, but unfortunately they are quite far from the zone we need.
Thank you very much, and let's thank the speaker once again.